Well, we're in the last section here. We're going to talk about the 68, 95, 97.7 rule. And the issue will be how long will it be that I can remember that. And then we're going to do normal curves as models of data sets and distribution of random events and statistical influence on inference. But before we do that, all right, back to what we're doing. Half of 68 is 34. Half of 95 is 475 and a half. Half of 99.7 is pretty close to 50. Okay. When we look at a bell-shaped curve, what's going to happen is that within one standard deviation, 68% of everything is going to be within one standard deviation, plus or minus. Within two standard deviations, 95% of the data is going to be there. And within three standard deviations, 99.7% of the data is going to be there. And if it's not, if it doesn't follow that rule, and we can give it a little slack, percentage on either side or so, then it's not a bell-shaped curve, it's not a normal distribution, and we can't use our rules. And so what we do, we say, well, within a z value of plus or minus 1, which is one standard deviation, we're going to have 32% either side of the mean. 30, that's half of that, basically. 32 one way. 32% remains. So 68% is within one standard deviation. 32%. Oh, there we go. Now we got some pictures. So plus or minus one standard deviation, 68%. What's left over, 16% either side. Two standard deviations, 95% is going to be there. That leaves us 5.5 either side. 2.5% either side. Wonder how much of this we're going to remember. 99.7 is basically everything. There's an itty-bitty bit left over, not very much left over at all. So if we grade on a bell curve, we'd expect the guys between plus or minus one standard deviation to get a C, and then that'd be bad with amplifications. For practical purposes, we rounded 99.7 up to 100. And there are no outliers in the data. If there's outliers in the data, up to 6 standard deviations, there shouldn't be any outliers at all. But then it doesn't have to normally be a bell curve. So our range is the max to the min. That 6 standard deviations should have everybody with no outliers. Oh, we're done already? Wow. That means we can work a problem. I suggest we do problem 31. Consider the normal distribution below. Find the mean in the standard distribution. All right, so 31. The mean. Looks like we have 98.8 plus 85.2 divided by 2. Does that look like the mean to you guys? Pretty much. $92 appears to be the mean. Now the issue is, what is the standard deviation? Okay, if 95% of the data occurs between those 2 points, that means we have 2 standard deviations this way and 2 standard deviations that way. So if I go 98.2 plus minus, where's my minus sign? Minus 85.2, and I divide that by 4, because I have 4 standard deviations.
Wouldn't it be
Plus 2 one
98.8?
side. Oh, I don't know. Yeah, is that better? Let's see. That's a 1. That's a 3. That's a 6. Well, I guess we can do that out here. That's 3.4, right? So my standard deviation is going to be 3.4. And that's the name of that tune. Find the first quartile and the third quartile. Okay, how am I going to find the first quartile? Oh, right. That the first quartile is the mean minus, is it 0.675?
675.
Is that it? 675 of the standard deviation. Good thing you guys are here, otherwise I'd forget these things. And the third quartile is the mean plus 0.675 of the standard deviation. Okay, so first quartile means 92, 0.675. That doesn't look like a plus sign, does it? And the standard deviation was 3.4, right? 3.4? Yes. Okay. And the third quartile, 92 minus 0.675, 3.4. Don't ask me this next week. I probably won't know it.
You have the plus and minus mixed up.
Did I do that on purpose?
Probably.
I doubt it. I don't recall doing that on purpose. 92 minus 0.675 times 3.4. Okay, 89.7. 92 plus 0.675 times 3.4. We'll call it 94.3. We don't know very much. We can't calculate very much, but the little we can calculate, we can calculate. That was 3137. If the normal distribution with mean mu, if a normal distribution with mean mu and standard deviation theta, what percentage of the data falls within mu plus 2 standard deviations between mu plus a standard deviation and mu plus 2 standard deviations? Okay, well, we draw our curve, and well, that's good. So 95% of the data is plus or minus 2 standard deviations, right? But we're not plus or minus, we're only plus. So that means, what's half of 95? 47.5. So 47.5% of the data will fall between mu and 2 standard deviations. So that's the A part. Now, we look at it again, and we say, well, we have something that looks like that. Here we have 2 standard deviations. We have 47.5% there. And now we want the, here's 1 mu sitting here, and we want the data sitting between those 2 things. So we want 47.5 minus whatever this is. The rule is a 68 rule, right? Half of 68 is 34. So if we subtract 34%, what's that, 4? 14.5%. 14.5% of the data is going to fall between
13.
mu, what?
13.
Oh, the other 13? Really? 4 from 7? Okay.
It's 3.
Yeah.
Okay. Is going to fall between the 1 standard deviation and 2 standard deviations. Okay. And it looks like the next problem is 43, which we probably can't do. Well, maybe we can do it. We'll see. We shouldn't be able to do, but we'll look at it anyway. 43. We have something with 2,500 students. Okay. And the mu on the test is 52 out of 100. It doesn't say that. I'm just saying that. And the standard deviation is 11. And we want to know, estimate the first quartile score. Oh, I can do that. First quartile, 52 minus 0.675 times 11. 52 minus 0.675 times 11. We'll call it 44.6. And estimate the third quartile score. 52 plus 0.675 times 11. And if I was smart, I should be able to do that without my calculator, but it's too late in the day. Not going to do it. We'll call it 59.4. Okay, well that was good. 47. For each of the following blood pressures, estimate the corresponding percentile. Number 47. Okay, so blood pressure mean is 120. Anybody greater than 125 in the room for their blood pressure? Anybody have a clue what their blood pressure is?
Like 116 over
Yeah.
78.
Yeah. So your age group, there's probably no one over 125, and I'm at 63, and I'm not 125. So, but my wife is up there. She helps out some. Anyway, back to what we're doing. What was it? And the standard deviation is 13. Okay, we want to know what percentile corresponds to 113. Okay, so we got something that looks like this. And that's 125. And when I add 13, I get 138, right? 138. And when I subtract 13, I get 112. And 112 sits right at the first standard deviation, right? Okay, so well, if 100% is the whole thing, and 50% is on this side, and 34% is sitting there. Is it 34%? I think it is. Half of 63, 68, right, 34%. Then this ought to be 112 millimeters ought to be at 100% minus 50 minus 34, or also known as
26.
26? No, 16. 16?
Or yeah,
16.
16. 16 percentile. So it's sitting at the 16th percentile. Okay. A done. B. 138. 138 was sitting there. So that's going to be 50 plus that 34. 50 plus 34, 84th percentile for B. And C is 164 millimeters. Okay, so come back up here. We're going to add 13, and when we add 13 more, we get 151. And we're looking at 64, and we add 13 more, and 13 more is 164. So that's at the 99.7 percentile, 99.7 percentile, because it is at 3 standard deviations out. Notice it didn't ask us for something that wasn't sitting at a standard deviation because we had no way to calculate that. Yeah. Okay. So that was 47. 49. 49. I think we should look at the next set of transparencies before we try 49. We probably should have done that before we tried 47 too, but it was more fun not. Okay. 6.5. Normal curves as models of real life data. You have nothing in real life that does it, right? Your bank account isn't a bell curve, right? Your insurance policy isn't a bell curve. The gas in your car isn't a bell curve, right? If it was a bell curve, it'd be at halfway most of the time. No, it's never at halfway. Anyway, but the author thinks we have real life things. So there must be some real life stuff here. Okay, useful real life stuff. That's even better. Approximate normal set plus or minus 1 standard deviation from the mean. Blah 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 blah. We said that before. SAT scores. I didn't even take the SAT, so. But standard deviation 114 points. Wow. We should do better than that. Our schools should do better than that. Just knowing the mean and standard deviation allows us to draw a conclusion about how useful the test is. Well, yeah, but I want to find out who the rocket scientists are. Medium. The medium and the mean should be the same in the standard deviation. Okay, well, that's fine. First quartile, we covered that already. Third quartile, we covered that already. College board, SAT scores, blah, blah, blah. Approximately 68% of the scores should fall between those two places, and they do. Isn't that nice? And approximately 95% do that. They do. And almost everybody scores within that. Isn't that lovely? That told me absolutely nothing. Sure, I'm glad we got through that, though, because now we don't have to put up with it anymore. Okay, coming up on distribution of random events. Now this is why you should stay away from the casinos, because the only purpose that they have in life is to take your money, and they do that quite well. Yeah. We are now ready to take up another important specter of the normal curve, and that happens to do with random events. And John who? Never heard of him. Prisoner of war during World War II, tossed a coin 10,000 times and kept records. The number of heads in groups of 100 tosses. The modern technology was repeated by a computer without tossing the coin. Okay. So we have a random variable x. It can either be a heads or a tail. It's either a head or it's not a tail. And we want to know whether or not we can do something with this. All right, that's fine. Extremely unlikely that x will be 0. So if I toss a coin 100 times, it would be extremely unlikely that I'd get no heads. It would be also, it wouldn't be unlikely, but to get right at 50 would be difficult too. although, but we get some number between 49 and 45 and 50 would do something else, right? So we should have some mathematical way to predict these outcomes, obviously. So this is our first trial, and we flip coins, and 100 of them, and we find 48 heads the first time, and then 49, 51, and we see that we have some distribution of times across there where we do it, and then we do it 100 times, and we see we get something like that, and 500 times, and we get something like that, and 1,000 times, 10,000 times, 10,000 trials. So there is a guy over here at 70. There's no one down there at 30 though. Do we go higher? Alright, so that means that we can predict if I'm going to flip a coin. Well, if I'm going to play Risk, right? I'm playing Risk. Should I attack or should I defend? What should I do? Normally, well, if I have the bigger army, I should attack, right? If I have the smaller army, I should defend, right? Well, the real answer is you should always attack, because the attacker gets 3 die, and the defender only gets 2 die. So if I have an army of 50 and you have an army of 65, I might be able to attack you and wipe you out. And I probably will, because I roll so much better than you do. No. But if I have an army of 45, I wouldn't want to attack an army of 90, because that wouldn't help any. I'd be wiped out. He'd outlive me. So those are just the way it is. First 10 trials produce a different result than the last thousands. Toy tossing experiment. Mean, standard deviations, times to do it. We're done with that guy. Maybe we want to work another homework problem. 49. If a 12-ounce bag of potato chips is chosen at random, what are the chances? Clearly, we have to have something other than what the problem is, right? In 49 through 50, packaged foods, blah, 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 blah. Mu is 12. Standard deviation, 1/2. Okay. If a 12-ounce bag of potato chips is chosen at random, what are the chances that it weighs between 11 and 13 ounces? Okay, well that's 2 standard deviations either way, right? So that's plus or minus 2 standard deviations of there. So it's a 95% chance that that's going to be the case. So that's the A answer. B, that it weighs between 12 and 13 ounces. OZ. Well, that'd be half of 95. 47.5% would be the chance that it would be weighing half as much. It weighs more than 11 ounces. C, more than 11 ounces. So that means it's going to be between minus 2 standard deviations and all the way up. 100 minus 2.5. 97.5%. Well, that was pathetic. Number 55. Could you guys do those? Could you do those? Those are okay? Yeah, okay. 55. This gets really complicated in the statistics class. I spent a whole 3 or 4 weeks trying to do these things because we try to do it not at a whole standard deviation. We're trying to do it we have Z tables that are 2 pages long of probabilities and oh, what a pain. Well, probably not that much of a pain, but yeah, what a pain. The distributed weight of a 1-month-old baby. Okay, so I got you 7.5 pounds. And the standard deviation, 1.1 pounds. 11 pounds, that'd be pretty bad. Suppose that a 1-month-old girl weighed 11 pounds. Approximately what percentile is she in? The best percentile. Oh, I guess that doesn't count. Okay, so here we are at 8.75, and here we are at 1 standard deviation, 9.85, and here we are at 2 standard deviations, 10.95, and here we are at 3 standard deviations, 11, 12, 12.05. Okay, so that's where we are. She's weighing 11 pounds. Well, that's almost there, right? 11 pounds. Okay, so at 11 pounds, there's going to be 2.5% left over going that way. So my A answer is she is in the 97.5 percentile. All right, now we're looking at B. Suppose that a 1-month girl weighs 12 pounds. What percentile is she in?
99.7.
Maybe we ought to round it up to, we'll go to 99.7. All right, we'll do that. I was thinking we should round it up to 100 percentile. But we can go with 99.7. Suppose that a 1-month child is in the 25th percentile in weight. Estimate her weight. Okay, so in the 25th percentile, right here we're sitting at the 50th percentile, and then down here, 1 standard deviation below, that's going to be 34 less, right? 34 less, 16%, and she's going to weigh 7.65, and she's in the 25th percentile estimated weight. Okay, so obviously she's between 7.65 and 8.75. And what do you think? 8 pounds?
Yeah.
8 pounds. There's no reason to have 8 point something because we're estimating. Yeah. So 1 significant digit is perfectly okay in an estimation. 59. Suppose that a random sample has 7,056 adults. I wonder how many children there are. 7,056 people claiming to be adults. How many adults are there in the room? Anybody? Yeah, that's what I thought. We're all kids, including me. All right, those adults anyway. Is to be chosen for a survey. Assume that the gender of each adult in the sample is equally likely to be a male or a female. Estimate the probability that the number of females in the sample is between there and there. Okay, I think it's time to move to the last transparency before we try to solve that problem. and hope that maybe, just maybe, we'll get a hint on how to do it. Statistical inference. Suppose that you have an honest coin. Oh, that begs issue. I got a coin. Okay. What can happen to the coin if I flip it? It can be heads or tails, or it could land on the edge, right? Or it doesn't have to come back, right?
Right.
If I flipped it in front of Scott, he'd grab it. It'd never hit the ground, right?
Right.
So those are 4 possibilities. So there might be other ones too, right? That we'd have to discuss quantum physics answers for the other ones. But those are the 4 possibilities that it could, like Big Julius in Guys and Dolls would play dice, he'd roll dice, and he'd roll dice without spots on them. He remembered where they were. That was good enough. Got a gun. He's Big Julius. All right, well, anyway. So x is a random variable, mu is 50, standard deviation is 5, blah, 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 blah. Okay, now, for starters, we can predict that x will fall somewhere between 45 and 50, 1 standard deviation, and above the mean is, plus minus, is 68%. Likewise, the chance of falling between 40 and 60 is 95%. Okay, that's fine. Even what if, instead of tossing the coin 100 times, we toss it n times? Not surprisingly, the bell-shaped distribution will still be there, only the values of mu and the standard deviation would change. For n sufficiently large, greater than 30, the number of heads of n is going to be that for an honest coin. Okay. Mu is going to be n divided by 2, and the standard deviation is going to be the square root of n divided by 2. But as n gets bigger, the standard deviation is going to get smaller. Let x denote the number of heads tossed. N is greater than 30. Then those 2 things are true. We just said that. Thank you very much. An honest coin is being tossed 256 times. What's the likelihood of getting a coin between 120 and 163? Should you bet on this? Okay, well, the standard deviation becomes 8. That means the value should be between 128 and 136. 1 standard deviation, blah, 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 68% of the time. Otherwise, it comes out something different. 95% of the time would be there, and close to 100% of the time, someplace between 104 and 192. Dishonest coin. Anybody have one of those?
I've seen them.
Yeah. So you could have a coin with 2 heads. I've seen one of those. Yeah. Works very good. And so a dishonest coin will not meet that criteria, and you'll see that something bogus is happening. So here's the dishonest coin. So the standard deviation is going to be the square root of the number of times I tossed, the probability of making it times the probability of not making it. So P is the probability of getting something, and 1 minus P is the probability of not getting it. All right, that's good. Probability of so. And but tossing a coin experiment, we're going to do the same thing. Going to do the same thing there. Central limit theorem. The dishonest coin principle is a special version of one of the important laws of statistics called the central limit theorem. We will now briefly illustrate what that means. An assembly line produces 100,000 light bulbs a day. 20% of them generally turn out to be defective. Suppose that you draw a random sample of 100. That X represent the number of things. What can you say about X? Well, you should get 4 light bulbs that are bad. You get 68% chance that you're going to fall between there, 90%, blah, 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 blah. Defective light bulbs, 4 standard deviations. Alright, so the sampling of the light bulbs, the number you have times the probability of it being defective times the probability of it's not being defective, square root. Alright, larger the sample, the better off you are. Boom, 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 boom. I think we're done. We're done? There, excellent. Back to homework problems. 59. 59. Where's 59? Suppose you have, already have it. Adults to be chosen, assume the gender of each equally sampled. Okay. We want to know the probability that the number of females in the sample is between there and there. Okay, what's the mu of this sample? 70, 56 divided by 2. 3, 5, 2, 8. What is the standard deviation going to be? What's the standard deviation going to be? The square root of n divided by 2. Because we're going to pick males and females fairly. Okay, so the square root of 7056 divided by 2. $42. Okay, now that we know that, got this here bell curve, and there's our one standard deviation, and it's going to be at 3570. And there's one minus the standard deviation, and it's going to be 3542 minus, that wasn't a minus sign, minus 42. 3,500. No, it isn't. No, it isn't. $34.86. 34.86. 34.86. 35.70. So the A guy is asking for plus or minus 1 standard deviation. What's the probability of being in there? 68%. Oh. Okay, that the number of females in the sample is less than 3486. Less than 3486. If 3486 is here, that means I have 16% on the bottom, right? 16% down there and 16% over here, because I have 34 left over, 32 left over. So the probability be that I have less than 3,486 females is 16%. The percentage of females in the sample, is below 50.6%. Okay, 50.6 of the mean. What's the mean? 3528. No. The total. 7056. So we want to know that number first. 7056 times .0, 3570. So now we know that we want that number going that way. The percentage of field is below that. Oh, they gave me a hint to find that number first. Okay, so that'd be 50% plus 1 standard deviation on this side of the mean, which is 34%, which gives me 84%. And that is the C answer. So we should mark it C. One more, and then we can go to the quiz. Which I don't think I put on the internet. Oh well, can't have everything right. 67. I hope that great big table is not used in 67 because I'm not sure I can see that far. Number 67. The distribution of weights for 6-month-old baby boys is approximately normal. Mu 17.25. Standard deviation 2. All right. Now what is this chart about here? Oh, okay. Yeah. You're next going to use the table above. Okay, that's what we're going to do. Suppose that the baby weighs in the 95th percentile. Estimate his weight. A. Well, if I'm in the 95th percentile, oh, there we go. 95th percentile is going to be mu plus 1.65 sigma. Okay, 17.25 plus 1.65 times 2. This is too easy. Of course, if I put the wrong number in my calculator, it won't matter that it's too easy. .6. All right.
That's a fat baby for 6 months. 20 pounds?
That is a definite. You'd probably call that a bruiser, right?
Oh, big time.
Maybe a big time bruiser. Yeah.
Oh, yeah.
Yeah. That is. Yeah, this data is probably made up. I think I was in first grade before I made 20 pounds, but I'm not so sure. B.
I have a 1-year-old and he weighs, 18-month-old and he weighs 20 pounds.
Yeah.
I have small babies.
Yeah. I have 2 grandchildren that are 19 months apart. And the first one was premature, and the second one was full term, and the second one's now bigger than the first one. And they're 5 and 4 right now. But when first babies are born, you probably know that you don't need any help, right? When second babies are born, you figured out you need help. So when the first baby was born, mommy wasn't asked to be there. And when bed rest was ordered, daughter didn't do bed rest. Daughter still went to work. Well, when it was time to do the second baby, mommy shows up, bed rest is ordered, daughter stays in bed, meals are good. They're not what are they? Pop-Tarts. Instead of having Pop-Tarts for breakfast, lunch, and dinner like they were having, they're getting fruits and vegetables and real meals, cooked. And second baby went full term. And pretty cool. Then they found names that are totally impronounceable. So, Anyway, you have 50, 50, 90, right? Suppose that a 6-month-old baby weighs in the 40th percentile. Estimate the weight to 2 decimal places. Wow. Okay, so 40th percentile, mu minus 1/4 sigma. 17.25 minus 1/4 of 2, which is a half, right? So that would be 17, way to go, Doug. That would be 16.75. And they wanted 2 decimal places, and we gave them 2 decimal places. And so all we need is a pound. And that makes us done with chapter, what chapter is that, 16? All right. So this
Can we
is,
turn it on homework today?
you could if you wanted to. You want me to put it, you want to grade in the grade book for it today too?
Sure.
No,
Oh,
not necessarily. I just don't want it in my notebook anymore.
you could do that. I don't see no technical reason why we can't. Thank you very much. We don't have to wait for Scott. Anybody want us to wait for Scott? No? Okay. Just one. Well, let's see. Anybody got a good answer for 1?
I guess maybe B.
So we got 1 vote for B.
B.
Hmm?
B.
Oh yeah, of course you want B.
B.
B, 3 Bs. Scott, would you like to give us the right answer? Or
C.
one vote for C. I don't know. Let's see. First of all, we have to find out where the mean is, right? So we're going to take 78 plus 30, and we're going to divide it by 2, and we're going to get a 54. So we got a 54 sitting there in the middle. 95% means plus or minus 2 standard deviations, right? So this 24 difference between there and there means that my standard deviation is 12. Okay, so if this were 12, which would be there, 12, that'd be what is it, 42? If I was at 42, my standardized value z would be at minus 1. So that's where 42 would be. And if I was at 30, that would be minus 2. All that being equal, that comes up with the realization that I'm closer to minus 1.25 than I am to minus 1.5. And I would have picked the answer delta if I was going to pick one. Okay. Problem number 2. Do we have any good answers? We can throw out that guy, right? Because that's obviously not it. It looks like we're at 100 for our mean, does it not? Yes, we're at 100 for the mean, and 50% of the area there, 50% over there. If it's 50%, oh, total area, both sides probably. Okay, so that we need 68% to have 1 standard deviation. So this is less than a standard deviation, that 27 is. So the standard deviation has to be greater than 27. All right, well, if it's greater than 27, and it's not 2 standard deviations, so it's got to be, well, I don't know. Let me rethink this. The one standard deviation would be out there. which would be greater than, yeah, I think I'd go with 40, B. Is how I would look at that. But it's not two standard deviations, because then that 54 would be two standard deviations out probably. Yeah, I don't, cancel that last thing. I'll go with B. I didn't ask any of you guys what you thought. I'm sorry. We're back to business as usual. Anybody got a good answer to 3? We don't even have all the 3 here. That's better. Cell phones. 1,850 said they own a cell phone. What's going on? Unbiased sample of the entire set. Estimate the standard error of the survey. Standard error of the survey. All right. Standard error of the survey. Is that the square root of 1,000 divided by 2? That'd be the standard deviation, right? 1,000 square root of 1,000 divided by 2 is 15.8. 15.8. The survey said 1,000 assume the survey was properly conducted, representing an unbiased sample of the entire population, the standard error. Okay, that has nothing to do with it. But neither did any of the transparencies we looked at. Darn. So much for the transparencies author. Thank you very much. Somewhere around 700 people give us a 5% error. So we can get rid of that, we can get rid of this, we can get rid of this, and now it's got to be one of those two. But there is a formula for calculating it. Where did it go? Margin of error in polling, page 600 and something. The standard error the standard deviation of the sample distribution of the proportion of voters in favor blah, 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 is called the standard error. For an example, we found that the below of the standard error is approximately 1, blah, blah, confidence level, blah, blah, blah. Standard error. What is the standard error? Okay, so we got to calculate the standard deviation, square root of the sample size times the probability that they say yes. 850 divided by 1,000 times the probability they don't say yes. 850 divided by 1,000. Okay. 1 minus 850 divided by 1,000 times 850 divided by 1,000
11.29. 11.29.
Okay, so this is 11.29. And then we take that 11.29 and divide it by 1,000, and what do we get? 1, 2, 3.
Some of the answers.
1, 2,
0.011291589.
0.01129.
0.01.
0.0129. When I change that to a percent, that's 1.1%.
Okay.
E. Okay. Thank you very much, author, for having that in your transparency group. Okay. Back to what we're doing. What were we doing? Suppose that 1 out of every 5 federal taxpayers, suppose that you can't even read the damn problem because it doesn't fit on the screen. Then what do you do? All right. Suppose submitted has an error. Out of 10,000 submitted returns, find the probability that at most 2,000 with an error. Okay. So we have 1 vote for B. Okay. Anybody else? Another vote for B. Brittany, of course, she wants B. Scott, you want to pick the right answer again?
B.
Scott picks a answer D. All right. So what do we got to do? We got to find the standard deviation, square root of the number of returns times the probability of getting an error, 1/5, times the probability of not getting an error, minus 1/5. So my standard deviation is 40. So my standard deviation is 40. You sure about that?
So I put into my calculator and that's what I came up with.
Square root of 1,000,
10,000.
10,000 times 0.2 times 0.8. Okay, 40. Okay.
I don't have $100 calculator for nothing.
Yeah. 1 out of every 5. Find the probability that there are at most 2,000. Okay, so here we go. There's our bell-shaped curve. Where's our median? Where's our mean? At 2,000. So one standard deviation down would be 2,000, 1,960, or 2,040 would be on the other end. Okay, so that'd be one standard deviation, and at most that. At most that. So we can't have them over there. 50% may. So at most would be only half of them. Probability of doing that would be a half. Excellent group. You guys did very well on that one. Okay. Consider a normal curve distribution before and assume P is the inflection point. Excellent. What is the standard deviation? Let's see, 115 minus 81. That's a 4, that's a 3. Echo. The inflection point is where the standard deviation is. Yeah. Yeah, you remember that one, right? I mumbled something about that 2 days ago, right? 3 days ago? Mumble, mumble, mumble. In a survey of 1,000 Americans, 5,800 said they, didn't we just do this one? Owned a cell phone. Assume that the cell phone, blah, 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 blah. Compute a 99.7% confidence interval expressed using percentages for the survey. Okay. So we gotta come up with a standard deviation again, right? Square root of 1,000, 850 divided by 1,000 times 1 minus 850 divided by 1,000. That was the 11.29. All right. So, got some curve. We're at 850, and we're going to go 11.29 either way. We want to go 3 standard deviations. If we want a 99.7, right, we're going to have to go 3 standard deviations. And so what does that do for our percentages? Hmm. 81%. Well, this guy's at 85%, right? So he's at 85%. Okay, so what's 85 plus 3 times 1.129? 85 plus 3 times 1.129, 88.3.
Only 88.4.
Yeah, but they probably dropped it because there is no 88.4. And if I go 85 minus 3 times 1.129, I bet you I get pretty close to that guy. I'm going to go with a C. Okay, now what we're gonna do something different today, because I think Brittany asked that we do something different, right? Because she's all for different things. So you're going to keep your quizzes, and I'm going to put the grade in the book, knowing that you are going to tell me that you got 100, right? Anybody not want 100 in the grade book? Okay, if you don't want 100 in the grade book, email me later because you're too embarrassed to have your friends know you don't want 100. Okay, but if I don't get an email from you by tomorrow at 16:34, then I'm not gonna do that. Okay, so what I'm going to do is I'm going to pass out the chapter 14 to 16 test so you can take it home. 1, 2, 3, I got 4 of them. Okay, that's good. And what we'll do next class period is we'll grade them, and if your grade is 90 or above, then that's good, we'll just keep it. If it's not, then we can have a second opinion. And then we'll go through the second opinion thing, and then after you give me your chapter 14 to 16 test back, then we'll do a take-home final. And then we'll do the same thing on Thursday. We're passing the take-home final grade it. If you need a second opinion, we'll do that. And if you don't, we won't.
Okay. That's doable.
That
We've
sounds like,
received all our quizzes, right?
Did I do what? Did I give them all back?
Yeah.
Yeah, I'm pretty sure I did. If I didn't, they're sitting here. Let's see. I have one here that says key, another one that says key, another one that's blank, another one that says key, another one that says key. I got one for Chris and one for Louise. Nope, I think I passed them all back. Yeah. Sounds like fun to me. And I suppose you could have a question and you could call me, but